All right. So I'll try to speak for half an hour. Let me stick the phone. What I'm going to do today is give you the presentation that I was planning to give at the March meeting. It was going to be an invited talk in which I was going to talk about time domain multiplexing and optimization of gate-based sensing for silicon-based quantum devices. Okay, good. So very brief recap of the state of the art of silicon quantum processors, just to give you a bit of perspective of where the field is going. Just to recall that the first demonstration of a spin qubit happened in 2012. And now the different steps such as initialization, single qubit gates, 2 qubit gates, and readout fidelities are approaching the requirements for error correction, for fault tolerance. The one aspect that is slightly weaker is the 2 qubit gates that only last year researchers in Australia demonstrated 98% fidelity. In terms of readout, the highest fidelity is done with single electron transistors. So this is worth to remember because we'll be talking a lot about readout, but the time scales to achieve those fidelities are a little bit short, a little bit long. Good. Just to show you an image of probably one of the most advanced silicon devices so far. This comes from UNSW, where you have a set of metallic gates on silicon oxide and then on silicon. These are standard MOS structures that are used to define a two-dimensional electron gas under the gates. In this central region, the gates are designed to accumulate electrons in localized areas, quantum dots. Then there is an electron reservoir. This green part is a single electron transistor, and this blue part is an antenna for delivery of microwaves to control speeds. So by looking at this, there are several things that we can say about how to take this one step further and scale it up. Probably in the future, we'll be doing this with CMOS technology, as we are doing in our lab. We are likely to want to get rid of the microwave antennas to simplify the architecture of the qubit by using, for example, microwave cavities, millikelvin temperatures. And then in terms of readout, probably we'll be wanting to get rid of the charge sensors to simplify even further the structure of the qubits. So the alternative to charge sensors is gate-based readout, and I'll be talking about that in the presentation. So in terms of specifications of what your readout should do, there are several things that your readout protocol should fulfill. One is that your readout method, or we need to understand that the minimum time taken to discern the state of the target system is what we are going to define it as T-min. So this is a characteristic of your readout method. And that T-min, you want it to be faster than at least the relaxation time of your system if you want to be able to discern between the two classical outputs of your quantum bit system. But for error correction protocols in quantum computing, you would like your T-min to be faster than the coherence time of the system, such as it will allow you to perform error correction. So characteristic T2 times in silicon are of the order of 20 microseconds. So that says the minimum integration time to be below or much lower than 20 microseconds. So that's a target. And then on top of that, you may consider footprint. So probably you like your readout method to be commensurate in size with the qubit if you are planning to read all the qubits. And then another option is to use a single sensor to read many qubits. This will not enable you to do simultaneous readout, but maybe you may want to use a sequential readout protocol. Good. So let's go into gate-based sensing. A bit of the state of the art on readout. Typically, readout in semiconductor systems is done with charge sensors, such as, for example, the single electron transistor, as we were talking before, is this brownish set of gates here that occupies some footprint on the chip. It's an indirect measurement because you are measuring a device that detects the state of a different device. And with this method, readout fidelities up to 99.8% in 65 microseconds have been achieved, but in timescales suitable for error correction, 97% is the state of the art in terms of fidelity. But there is another approach that doesn't require to have a sensor on next to your qubit for readout, which is dispersive readout, any typical implementation of circuit QED. In this case, this approach has been used, for example, by the group in Delft, achieving a readout fidelity of 98% in 6 microseconds. The advantage of this is that it's a direct measurement, so you don't need to use an additional device to sense the device that you want to detect. But you can see that, for example, this resonant method that involves a resonator, as you can see here in this picture, occupies some substantial footprint. There is another approach that it's basically within the context of circuit QED, as well on the context of dispersive readout, that we like to call gate-based sensing, in which basically you co-integrate two different technologies. One, for example, gallium arsenide technology that defines quantum dots with superconducting technology, or the definition of the resonator. So this doesn't interfere with the footprint of your quantum system. It's, as we said, a direct measurement. But by having these two systems separated, researchers so far have only been able to achieve a modest fidelity of 83% in 300 microseconds. So we will see what we can do about this in order to improve it. So the way dispersive readout works is that you embed your quantum system in an electrical resonator formed by an inductor and a capacitor, and that's coupled to a probing line by a coupling capacitor. Typically, the devices that we test are double quantum dot systems like this one. This is a schematic representation of 1 and 2 quantum dots that are capacitively coupled together and probed by a single input here on the top. And this, we know very well that at low frequencies and low temperatures, this is nothing but a variable capacitor. So we can study this in a circuit description quite nicely. Good. So the way this works, since this is an electrical resonator, has a particular frequency of resonance given by the inductance and the total capacitance of the system. Now the total capacitance is composed by the capacitance of the device under test. And in that case, the reflected phase has a sudden shift at the resonant frequency that we can use for detection. So for example, if the qubit is in state 0, we are going to have a particular phase when we measure at the drive frequency and a different one when the qubit is in state 1. Good. We've analyzed this problem quite carefully and extracted the signal-to-noise ratio, which is nothing but the change in reflected power between state 0 and state 1 of your qubit divided by the noise power of your system. And in the small signal regime, the minimum integration time, so this is the time you need to integrate for an SNR of 1, has this particular formula, which will enable us to improve the sensing method. So things that matter here are how well your resonator and the external line are coupled. This is the coupling coefficient, beta, and this becomes minimum when beta equal 1. Then the noise temperature of your amplifier, you want to minimize that. You want to maximize the gate coupling ratio, alpha. And then also you want to minimize the total capacitance of the system, operate at higher frequencies, and maximize the internal Q factor of the resonator. Good. So in terms of experiment, how do we do all those improvements? So one is to work on the gate coupling, large gate coupling. And in order to do that, something that we've been using for a number of years now is to use quantum dots in tri-gate field effect transistor technology, these devices that you can see here from Leti, where if we take a cross-section along the gate of that transistor, you can see the silicon body of the silicon nanowire and the gate that wraps around the three top faces of the nanowire. Dots form are the corners, and because of this three-dimensional geometry, the wrapping and the control of the conduction band in that region is quite efficient. This gate coupling, that is nothing but the ratio between the gate capacitance and the total capacitance, is interesting to note that is strongly linked with the expression of the subthreshold slope that the semiconductor industry has been trying to optimize for decades. So that's why it's very interesting to try to use these CMOS type devices. So typical gate couplings that we observe are of the order of 0.85, 0.95, and this is because of the 3D geometry, the high K oxide that results in a very small equivalent oxide thickness, and also the thin silicon insulator. Good. We also want to increase the internal Q factor and achieve good matching. So we need to modify a little bit the way we do this type of reflectometry measurements, whereas before the community used to do these measurements in series with a typical Q factor of the order of 10 to 100, dominated by the losses in the external circuitry. Now we do this in a parallel resonator configuration in which we decouple the external line from the resonator. The coupling capacitor enables us to control the coupling quite well, and we can as well optimize the arrangement, such as we maximize the internal Q factor. Good. So we put all these ingredients in a single experiment quite recently, in which we combine several of these concepts as well with a low temperature amplifier, actually a Josephson parameter amplifier. So let me guide you through the experiment. So this is the setup that we use for the experiment. We have these silicon nanowire transistors, and in order to have a internal high quality resonator, we use these niobium nitride on sapphire inductors that we produce ourselves. So that appears here in the circuit. They have low internal loss and low parasitic capacitance, which helps. And then we probe the system with an internal, with a tone that comes to the resonator, bounces back, and then the particularity of these newest experiments is that that is amplified by a Josephson parameter amplifier, and then followed by cryogenic amplification. This is more standard amplification. So this is the spectrum of the resonator at around frequencies of 620 megahertz. You see the reflection coefficient and the phase response of the resonator. So we can see that the matching is relatively good, and the Q factor is approaching the value of 1,000. So this is the internal Q factor. Good. This is the amplification profile of the Josephson parameter amplifier. So we can tune the frequency in which the Josephson parameter amplifier is going to amplify. We tune it into resonance or almost resonance with the resonator. And you can see the gain. There is a small reduction in gain here at the resonant frequency of the resonator because the resonator is not perfectly 50 ohm match. Good. So that gives us of the order of 15 to 20 dB gain with the JPA. And then we can see the effective noise temperature of the resonate of the system in two particular considerations. One, when the amplifier, the Josephson amplifier, is off, we have a noise temperature of the order of 2 Kelvin to 3 Kelvin. And then when we switch on the JPA with this additional gain at lower temperatures, we achieve an overall noise temperature of 250 millikelvin. Okay, which is, as you can see, an order of magnitude improvement over previous amplification schemes. Good. So we go, we tune our device using the top gate and the back gate voltage into a region in which we have an interdot charge transition. This occurs by chance in this particular device, and this interdot charge transition is between a dot and a dopant that is in the channel of the device. So this is the transition that we want to measure when doing spin readout, because we will do a projection between the 1-1 state into the 2-0 state of the spin states of the system. So you can see the signal in 4 different configurations. First, when the JPA is off for 2 different integration times, at 1 microsecond, the signal is barely resolvable. But when we turn on the JPA, you can see that the noise level goes down quite nicely, and then we have a sizable signal to noise ratio. So we benchmark this methodology, and we can see that the minimum integration time without the JPA is of the order of 1.2 microseconds. When we turn on the JPA, that goes all the way down to 80 nanoseconds. It may be a bit, so this is quite a substantial improvement over other designs. But there is one particular aspect that needs to be improved, and we will do in the future, which is to increase the bandwidth of these resonators, which at the moment are of the order of 0.65 megahertz, and ultimately will limit the speed at which we will be able to resolve single spin signals. Good. Those minimum integration times translate into fidelities of the order of 99.7% in 32 microseconds without the JPA and 1 microsecond with the JPA. Okay, so to put these results into perspective, we can check last year's high impact papers from UNSW, for example, that achieve a 73% fidelity in a millisecond. That takes a bit of time. Then an 83% fidelity in 300 microseconds, an improvement by Simon's group. And ultimately, the best demonstration from Delft with a fidelity of 98% in 6 microseconds. So our results should, in principle, allow us to defeat these values obtained with these bulky on-chip resonators. Good, so first conclusions, gate-based sensing, in which we separate the quantum devices from the microwave circuitry, enables us to optimize both the devices for optimal gate coupling and the superconducting chips for lower loss performance. Also, if we operate at slightly lower frequencies than the circuit QED approaches, we will be able to measure transitions with lower tunnel rates compared to what others are measuring. And what we can see is that the readout times and fidelities are required for silicon qubit readout. Good. Okay, I think I have another 10 minutes, so I'll be talking about how scaling gate-based sensing can be done. So in silicon, we always talk about being the platform that provides the highest integration density of all the solid state and non-solid state systems. You can see here the length scales of a quantum dot that are of the order of less than 100 nanometers by 100 nanometers. So in principle, silicon could provide a density of 10 to the 8 qubits per centimeter square compared to superconductors and on-chip ion traps that have a much lower density. The problem is that if we use this type of superconducting resonators for circuit QED, or even the spiral inductors that I've demonstrated, then the densities of silicon drop down to the densities of other competitors. So there is a necessity to do something about the footprint of this readout method. There is a very nice proposal from Menno Belhorst that suggested using a DRAM approach, so dynamic random access memory approach, to control and readout of silicon spin qubits by integrating quantum devices with more standard digital devices. Just to tell you a bit more about classical dynamic random access memory, those are constituted by a two-dimensional array of capacitors, that's your bit, and control transistors that can be activated by a series of word and bit lines. So you can address a single unit in that array. So in that particular paper, they propose adapting classical DRAM approaches to read and control multiple quantum dots and read multiple quantum dots with gate-based sensing, as we've shown before. So our response to that proposal, that theoretical proposal, was to demonstrate the proof of principle of that approach and try to see if we can read more than one qubit with a single resonator. So how do we do that? With this particular scheme that we have here on the left-hand side. So we have our quantum devices, like the ones we've seen before in the presentation, that are interfaced by control transistors that are fabricated on the same chip using the same fabrication technology, and they interface the quantum devices with a single resonator. So it's a transistor-based solution that in which we have quantum dots on narrow FD-SOI transistors and control field effect transistors on wider FD-SOI transistors. I'm going to show sequential gate-based readout with this approach, in which we'll be reading one transistor as we access that using the control transistor 1, and then we'll move to the second one. And the advantage of this approach is that you just need one resonator per row, and you have also a single control line per row as well. So you minimize the number of resources that you need to control a number of qubits. This is our proposal, for example, of how that arrangement will scale, in which you can see, again, recognize the DRAM cells that are now interfaced in the column with a single resonator, in the row with a single resonator, and in the column with a single access single voltage for control of the access transistor. And the readout should happen in this architecture via both time multiplexing, time domain multiplexing, and frequency multiplexing. Good, so I'll be talking about the subset of the array. Okay, experiment-wise. So as I was saying, we use narrow transistors for the quantum dots with a width of 60 nanometers, and wide transistors for the control FETs because we wanted to minimize the on-state resistance. You can see here a measurement of the Coulomb diamonds of one of these quantum dots here, where we vary the data line voltage here, effectively the gate voltage, and the source drain voltage of that quantum dot. Okay, so this is the frequency spectrum of the resonator. When we activate one, in the blue case, we have the spectrum of the resonator. No cells are activated. We have a particular resonant frequency there. And then we activate one of the cells, in this case, the orange one, frequency drops down because of the additional capacitance, or we turn on the other cell. That's the green trace, frequency goes down as well because of the additional capacitance. If we even turn the two on, frequency goes even lower because of the addition of the two capacitance. The most important thing here is that when we turn one of the cells or the other, the resonant frequencies overlap because we are going to do time multiplexing. We want to be using the same frequency all the time to address as many qubits as possible, but in this case, two. The spectral overlap limits the bandwidth of the measurement, and in this particular case, since we are not using superconducting inductors, we are talking about quality factors in the off state of 100 that drop to 40 when we turn on the word line transistors. Okay, so this is the phase response of the resonator on the first cell when the cell is activated and we sweep the data line voltage. You see several Coulomb oscillations. And this is the response of the other cell when we sweep the data line and measure the frequency response of the resonator. Good. A bit on digital inputs and variability. So we need to assess what is the word line voltages that we need to apply to these control transistors to be able to read or not on demand the quantum devices. So you can see that at low word line voltages, there is nothing to read, but as we pass the threshold regime of the transistor, eventually we can start to see the Coulomb oscillations of those devices. This is for cell 1, and this is for cell 2. Look at the similarity of these two plots, showing the low variability in the on and off regions that are going to be used for sensing the quantum devices. Good. Yeah, this is a summary. We will be operating on the on state for word line voltages above 0.9 and off state voltages below 0.7. Good. Okay, so this is the scheme that we use for time division multiplexing. Just follow the time sequence here, in which first we turn on the word line 1 to activate the control transistor, and then we sweep the data line voltage that enables us to read those Coulomb oscillations of the one quantum dot. And then in the second period of the cycle, we turn off the word line 1 and switch on word line 2. And then now, as we sweep the data line voltage, we can read the state of the other quantum device. So we can do this dynamically for different backgate voltages and extract the stability map of device 1 and device 2 in just a few hundreds of milliseconds. All right, good. So I'm almost finishing. Just to say that this was an experimental proof of principle of time division multiplexing, but there are many parameters that are subject to optimization. In order to do a proper optimization, you need a nice circuit equivalent of your unit cell, which contains the circuit equivalent of your quantum device, a storage capacitor, field effect transistor that is used for accessing the quantum device, and your resonator. You can do an optimization based on your RF sensitivity, say your storage time, the noise on the gate, and the footprint. And in order to do SNR optimization, we just use the formula that I presented in the first part of the presentation with a set of parameters given here. What we find is that the more relevant parameters that one needs in this optimization process are, one, the width of the control transistor that determines both the resistance and capacitances of the control FET, but also the footprint, and also the size of the storage capacitor that will ultimately limit the readout time on a DRAM type of way of operating this system. So what we find is our measurements are above an SNR of 1 for a bandwidth of 250 kilohertz, so for microseconds readout time. But in principle, you could make your transistor smaller and preserve the signal-to-noise ratio if you were willing to sacrifice the storage capacitance value, hence sacrifice storage time. Good. Okay, so a suitable unit cell for DRAM architectures is presented in this schematic here. So considering quantum dots that are going to have 100 nanometer pitch between them and trying to achieve an SNR of 1 or larger than 1 at 4 microseconds integration time, much smaller than the T2 star of silicon, we find that the best parameters are a control transistor that has a commensurate side to the qubit footprint. That will be a transistor with a width of 100 nanometers and a length of 20 nanometers. And a capacitor, a 3D capacitor, 2 microns in height, but will potentially have a 25 femtofarad value for that capacitance. That can be done in DRAM 1X technology. in the 14 nanometer node that is already in commercialization. Good. So with this, I will conclude and say that we are combining in this latest experiment 3 elements that most likely will play a role in scalable silicon-based quantum processors: quantum dots, field effect transistors, and gate-based sensing, quantum, digital, and analog electronics all together. And in terms of optimization, there are things that we are working on optimizing, such as charge injection and clock feed-through that I don't have time to explain. And we will want to show a combination of time and frequency multiplexing on 3x3 qubit arrays to demonstrate the reduction of the number of inputs following. And we want to do all this with integrated circuit and integrated circuit approach. Good. So yeah, so this is not the work of a single individual. This is the work of many people, like James, Sunye, and Lisa. Hitachi, also Sylvain, fabricated these very good devices that we use for these experiments. Some of this work came in collaboration with the Quantum Spin Dynamics group, Simon Sal, Virginia Ciriano, and John Morton in London, members of the University of Cambridge, like Imtiaz, Alessandro, Changmin Lee, Mario, and Jason, and the JPAs were from Siddiqui's group. Okay. Thanks for the attention. And if you have any questions.
Thanks very much, Fernando. Yeah, maybe does people have questions?
Fernando, can you hear me?
Yeah.
So on one of the slides, there was a graphic with, I think it was towards the end of the slide, so looking at the DRAM cells. So kind of versus the voltage applied to the word line, maybe here. Oh. So I think there was a plot where you measured something like some sort of spectrum versus the voltage. Here we go. Yeah, this is the one. So on the left-hand side, the green graphic.
Yep.
So I guess each of these peaks corresponds to some sort of charging threshold.
Yep.
And on one of the lines, I guess what you would hope is that this would be independent of the word line voltage above the threshold.
Yep.
But there seems to be a little bit of a variation on the middle line.
Yeah.
That might be. Yeah, that one there.
Yes. This is a switch that occurred in the device, in the quantum device during the measurement.
Okay.
So, a switch, I mean a charge fluctuator. In principle, in all the majority of the measurements that we did, these lines are completely vertical because the effect of the word line above certain threshold has no effect on the performance of the quantum device. So what we see here is a charge switching in the device that shifts slightly the position of the peak that occurred during the measurement. Yeah.
So in other words, the take-home message here is that there's no kind of non-linearity where the voltage that you're applying depends on the word line at all. It's just on or off.
Yeah, yeah. Only when you do things dynamically, because there is this mechanism that I don't have time to explain called charge injection. Sometimes when you switch on and off the control transistor too fast, if your design is not optimized, you may inject some of the charge from the control FET onto the gate of the quantum device, and that affects the effective voltage that appears on the gate of the quantum device, at least for a period of time.
Okay, thanks.
Any more questions? Maybe I can ask a question then. Well, like, so this the schematic from Velhorst. Can you show this? So is this integrating where is the resonator integrated in this Is it similar to what you showed with the vertical capacitor, or is this different?
So there is no description of how that will happen.
Okay.
But I guess the vision there is, let's fabricate the quantum device, which is this bottom layer, and the control transistor, which is this other layer here, all with CMOS technology.
Yeah.
That's going to be very hard. So let's not make it even harder by putting the resonators. So you make that on one chip, and then the resonators, you make them in a different chip.
Okay.
And you make an hybrid of both by, say, bond wiring or flip chip.
Okay.
Yeah.
But you think that you can get what with 25 femtofarads with a
Yeah, I know what you mean. So we talk about the resonator.
Yeah.
Now we talk about the storage capacitor. In this,
okay. Yeah.
In this description,
yeah.
Unfortunately, the footprint of the storage capacitor was not properly accounted for.
Okay.
They were talking about 1 picofarad capacitor that was necessary there. That's huge. That has a very large area. But nevertheless, it was a very good proposal. What we did is to just check what is available in terms of the modern technology. Of course, we are talking about much smaller capacitors because as soon as you go large in capacitance, the footprint becomes also unmanageable.
Yeah.
But these vertical capacitors are already manufactured. They use this type of structures for DRAM in this particular technology called DRAM 1X. And you can have that very small footprint of 100 by 20 nanometers.
Okay.
Yeah, maybe 100 by 40 nanometers. But you see here there is a lot of work to be done in terms of vertical integration, because here you have the quantum dot, and what we are doing here is just positioning the control transistor, that's the planar stuff that appears there, and the capacitor in line. Okay, and then you have the word line controls the gate, that's the blue cylinder, and the data line is used to connect the source of the transistor, the drain, sorry. And then the source should connect to the gate of the quantum device.
Okay, thanks.
Fernando, I guess one of the scale-up problems that you also have is kind of in terms of the gate voltages applied to your the qubits.
Mm-hmm.
Is this kind of architecture that you have, is it compatible such that you can also tune this kind of DC gate voltages on the device using this DRAM as well?
Good point. So maybe let's use this image. For example, the data line is in this arrangement is shared between two devices.
Okay.
The vision is you load the data line with a particular voltage, and then you open the word line, and that voltage will appear on the quantum device 1.
Okay.
The voltage that you need for this particular FD-SOI technology is of the order of 0.5 volts, so quite compatible with industry standards. And then you disconnect from the data line, and then you go to the next one, and you provide a slightly different data line voltage if you need onto the second device. The caveat there is that the voltage here, while you are not connected to the data line, will vary over time. So you need to manage that voltage variation over time and assess whether you can cope with it. But in principle, you have the flexibility to send data line voltage on demand to each quantum dot if you wanted to.
Oh, okay. So this is also compatible then with the readout scale up as well. Yeah.
Yeah, if you don't care about data line and you care about the resonator, I think the advantage there is quite nice, because in principle, what this allows you to do is connect and disconnect from a single resonator whenever you want to read a device. So in that case, there is no problem of voltage drop on the gate if the only thing that you want to do is read. I think the advantages there are a little bit greater if read is everything you care about.
Okay, thanks.
Any more questions? If not, yeah, thanks very much, Fernando. Thanks for being brave enough to go first, and yeah, that was really good.
Very good initiative.
Did you feel like it was okay to give the talk? And
yeah. I mean, I like it to give the talk on the screen because you can see the slides quite well. You're not when you're giving a presentation, you have the slides behind you.
Yeah.
So it's good. It's fine. Good.